All right, welcome to section 6.2, multiplying and dividing radical expressions. So the question you may have came up with yesterday is, what if I can't take the square root perfectly or the cube root perfectly? What am I going to do? How am I going to figure this out? Well, before we get into these examples, here's an overview of what we're trying to do. I have the cube root of 24. I can't take the cube root of 24 because I mean, you can use a calculator and get a decimal, but that's not considered simplifying. So you have to split it up into what you can take the cube root of and what you can't take this cube root of. Kind of like what we did in the chapters where we had the quadratic formula and stuff like that. Like I remember a thing where we had the square root of negative 108. That was like on the last test, and we had to split it up into three things, right? We had to split it up into three radicals. We did negative 1, 36, and 3, and so it was 6i radical 3. That was like on the last test. We had to split up. But now, instead of just square roots, we're going to do a cube root. So you're going to split this up into two cube roots. Okay, well, I made it small numbers, so it's not too hard to figure out here. It's 8, right? 8 is a cube root that lives inside of 24. So 8 times 3 is 24. So this becomes 2 cube root of 3. So the cube root of 8 is 2, and then the cube root of 3 you can't do anything with. Kind of like how over here we could take the square root of this, so we could take the square root of that, but then that guy was left behind. So we're doing simplest radical form, but we're going to do simplest radical form with cube roots and fourth roots instead of just square roots. All right, so on with the examples. Multiplying and dividing radical expressions. Again, you can stop this and to write something down, pause it as much as you want, contemplate, think, all that good stuff. And we get to sing the song, Mr. Jackie, and all the students know the exponents E-I-E-I-O today. All right, so here we go. Big numbers. So basically, we're going to multiply the two big numbers together. We have the fourth root of 125 and the fourth root of 405. So I get out my handy dandy calculator here, and I'm going to multiply. Oh, I minimize this so it's out of the way. So I'm going to multiply 125 times 405 equals 50,625. So this now becomes the fourth root of 50,625. Now, on your yellow paper, if you go in the fourth column on your yellow paper, guess what? That number's there. So how was that number made? Well, it was made by multiplying a bunch of 15s together, right? 4 15s to be precise. So 15 times 15 is 225. As I'm talking to you, I'm looking at the colored paper right now. So 15 times 15 is 225. And then 15 times 15 times 15 is 3,375. And then four of them, 4 15s multiplied together is this number. So the answer is 15. All right. So there's example one. We multiplied two radicals together. The dividing ones, those are the pain. When we do the dividing, I may melt your brains, so be prepared for that. Division's always the hard thing, isn't it? All right, so here we go. We're going to break this up. We're going to take out the largest perfect cubes. We're going to take out the largest perfect cubes. We're going to split it up into what we can take the cube root of, what we can't take the cube root of. So here we go. Cube root and cube root. So you're like, well, how do I know what to divide out? Well, let's just start dividing by perfect cubes. So I'm going to go here, and I have my colored paper in front of me, and I have 135. 135 divided by. Okay, well, the first perfect cube that I see that's smaller than 135 is 125. Well, that doesn't divide in there evenly, does it? No, it divides, hey, to a nice decimal, but it doesn't divide evenly. So then I drop down. What's the next one? Oh, 64. 64 is a perfect cube. So I do 135 divided by 64. Does that work? Nope. I could have told you that. It didn't work in the first place. Now we go to the next one, 27. 135 divided by 27. I think this one has hope. Yay, 5 times. So we're going to split this up into 27 times 5. So I put the good perfect cubes in the front slot and I put the junk in the back, just like we did when we simplified the radicals with the quadratic formula. Now, Mr. Jackie and all the students know the exponents E-I-E-I-O. This is the index and this is the exponent. Wait, I just said that backwards. That's the exponent. This is the index. Woo! Backwards. So I'm going to try and divide this in there, right? Because you take the exponent and you divide it by the index. So does 3 divide into 5? No, it doesn't divide in evenly. So you drop the power down. Does 3 divide into 4? No. Drop the power down again. Does 3 divide into 3? Yes. So I break out 3 of them. So I do x to the third and x to how many times I dropped it. And I dropped it twice, right? Now, you should be aware that if you multiply these two things together, it should make the original, right? 27 times 5 is the 135. And then when I multiply x to the third and x to the second, I get x to the fifth. But you see, I've sieved out the golden nuggets, right? These numbers are perfect. All right? They should have like little sunbeams radiating out of them. Those are the perfect numbers. Looks like some kind of deformed insect now, doesn't it? So these are the perfect numbers, right? Um, Here we'll make him jump out at you. Whoa! Or we can do this. We can make a rectangle around it, make it pop out of the page. Yes, those are perfect. Woo! So I sorted out the perfect numbers, the perfect cubes in this case. So now I go ahead and take the cube root. The cube root of 27 is 3. 3 times 3 times 3. Now we do the E-I-E-I-O thing. The 3 divides into the 3, x to the first. I don't really need the 1 there. And then this is the leftover junk. Boo, boo, junk, junk, yuck, yuck. I can't take the cube root of any of that, so I just copy it down. Cube root of 5x squared. And that's the answer. All right, so let's look at this full screen. I broke the perfect cubes out of the 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 number there. I took out the perfect cubes. They they were factored out to the front. And then the leftover stuff was left behind. How did I find the 27? Well, I just tried the different perfect cubes until I found that 27 does indeed divide into the 135. And then I dropped the index or the exponent twice because I tried to divide the index in there. All right. Next example. We're going to multiply, then simplify. So we're going to multiply these together, then simplify. So here we go. 50 times 48. It's at the end of the day. My brain's tired, so I'm going to get my calculator here. Times 48, even though that shouldn't be too hard to do, is 2,400. Whoa, 2,400. I kind of jerked on my cord here, make sure that it's still plugged in. Okay, we're good. You don't want to lose. You don't want to lose me on the audio, do you? Um, or maybe you do. I don't know. 2,400. So multiply the numbers together. This is under a square root, so it's 2,400. All right. Then multiply the x's together. X to the fifth and x to the second is x to the seventh, and y to the sixth. All right, the index is 2. Now we're going to build ourselves two radical symbols. We got the first square root and the second square root. So we're splitting it up into what we can take the square root of, what we can't take the square root of. If you look on your colored paper, you can go all the way to the bottom of it. There's a perfect square that we can use here. That's 400. All right. And it's 20 times 20. And I know if I gave everybody in this room 20 $20 bills, you could all count it up really fast and tell me that you had $400. 20 $20 bills is 400. So here we go. So we're going to split this up and we're going to take 400 out because that's the perfect square. So 400 times what? Well, 4 times 6 is 24, so it makes sense that it'd be 6. All right. Now we do the E-I-E-I-O business. Does the 2 divide into 7? No. So we drop it down a power. Does 2 divide into 6? Yes. So we write x to the 6th power. And I dropped it down once, so there's 1y left over. Does 2 divide into the exponent 6? Yes. So I take the whole thing out to the front because it is a perfect square. So the good stuff is in the front, right? And the 6y is the junk. It's left over. And again, we found the golden nuggets that live inside of there. Let's get the creative pen going here. Let's make stars fly out of this. Woo, 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 woo. That's the good stuff right there. Those are all good, awesome numbers. I can take the square root of each one of those numbers and variables. And then the six, the 6y is like, eh, yeah, I can't do anything with that. Let's see. Can I find an awful? Where's that awful? We got the pen. Oh, I know what we can do. It's that awful green. All right. Oops, that's the wrong button. I don't want that button. Um, I got this button here. You guys know that green I'm talking about? This one right there. Yeah, 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 yeah. Right? That's just gross. Okay. So here we go. Back it up, back it up, back it up, back it up. There we go. And proceed. The square root of 40, or 400, I just talked about that. If I gave you 20 $20 bills, you could count it up. So 400 would be 20. And then we're cutting these exponents in half, right? Because you take the index right here and you divide it into the exponent. So it's x to the third and y to the third, square root 6y. All right. What a whale thing. So the answer is 20x to the third, y to the third, square root of 6y. Next example. Ooh, division. Division, 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 division. So now I just divide, okay? And I divide and I see what's left over. So I'm going to make one radical home here. And that's just the radical symbol. And when I add the 3 there, then that means that it's cube root. So I'm going to take 189 and divide it by 7. So that I don't mess this up, I'm actually going to do it. 189 divided by 7 is 27. Well, that's good. That's good news. 27. 27. And then x to the 7th and then x to the 2nd would be x to the 5th, because when you divide like bases, you subtract exponents. All right, now we're going to sort it out into what I can take the cube root of and what I can't take the cube root of. Can I take the cube root of 27? Hopefully you're all going yes, so I put 27 in the front. Does 3 divide into 5? Because remember, the exponent has to be divided by the index. Does 5 divide by 3? No. So I drop it down a power. Does 3 divide into 4? No. Does 3 divide into 3? Yes. So I make it x to the third and x squared. So the good stuff is here in the front. The cube root of 27 is 3. The cube root of x cubed is x. And then there's a leftover cube root of x squared. All right, example 5, I think we're going to deal with when I get back because it scares me, and I'm afraid that um, I will melt your brains trying to explain that on a video. We're 14 minutes in. That's a pretty good clip, and that's most of the lesson. So this is the assignment. It looks crazy long, right? But it'll keep you busy and happy doing math problems. Okay, so it's the odd problems on this page, 11 through 51, 11 through 51 on this page. So it's really, it's not that bad. Like the first one here is like number 11, cube root of 4, cube root of 16. This is like the first example I did. You multiply those together, 4 times 16. Now remember, guys, remember when I was in elementary school, they taught me how to count by 16s. So 16, 32, 48, 64, right? So 4 times 16 is 64. So this is just the cube root of 64. What is the cube root of 64? It's on your yellow paper. It's 4, right? So the problems can go pretty quick like that. Don't freak yourselves out. Take a deep breath, give it the old Harvard try, and let's see what happens.